Hi everybody, welcome. This is your homework for tonight, chapter 11, lesson 1. We're going to be looking at geometry and polygons. So some of this will be a review of shapes from what you've known before, but we're going to be putting it together in new ways for 5th grade. So let's take a look. Remember, this is your video that goes with your homework pages 641. You're going to be doing problems 1 through 8 and 642 all. As we go through it, we'll have a lesson first, and you'll give these problems a go on your own, and then you can check the answers with the video as it goes along. So as you see the pair, go ahead and stop, do the work, and start over to see how well you did. All right, by the end of this lesson, you'll be able to explain what makes a shape a polygon rather than a just traditional shape, and you'll be able to classify polygons into common features. All right, so how do you identify and classify polygons? That's what I want you to think about. Have you done that before? Go ahead and put in an answer, just what you think. Is there any words that you're not sure about? Go ahead, or any questions you have, you can enter those too. So not only do you have to be able to identify them, what do they look like, but you have to be able to classify them and sort them based on common features. And that's our higher level kind of thought for today. So this is our vocabulary for this chapter. I'll be introducing some of them. I'll be introducing the words and then talking a little bit about some of the shapes each day. So we have our polyhedron, our polydro, a solid figure with faces that are a polygon. So it's not just a two-dimensional shape like this triangle or square, but it's actually a three-dimensional shape that can hold capacity, that volume. All right, so the parts that make this 3D figure up are also a polygon. So that's what makes a polyhedron. A prism is a solid figure that has two congruent polygon-shaped bases and other faces that are all rectangles. So you've seen these before, these prisms. And you can have some prisms that are rectangular prisms, but you can also have a triangular prism that has a rectangle base, and that would be a triangular prism. So then you have a pyramid, a solid figure with a polygon base. There's your square, see it right there, your four sides. And all the faces are triangles that meet, and all the other ones are triangles that meet at a common vertex. And we'll talk about these points, vertexes. Quadrilateral, a polygon with four sides and four angles. A regular polygon, a polygon in which all the sides are congruent. That means equal distance. They're all the same length. And all the angles are congruent, which means they're equal. And I don't know why they're now using congruent versus equivalent with the root word equal, but they are. So this is a new word for us, is congruent. Scaling triangle, a triangle with no congruent sides. That means none of them are the same length, or none of the angles are the same size. Unit cube, a cube that has a length, width, and height of 1 unit. So this unit can be an inch or a centimeter or a meter or a mile. It can be something as small as a millimeter or an inch. But each of these lengths are exactly the same unit. So if it's 1 inch, they're all 1 inch. If it's a centimeter, they're all 1 centimeter. That's your unit cube. If you don't want to identify it as any form of measurement, then you can just call it a unit. Volume, the measure of the space that a solid figure occupies. So whatever, we also, it's kind of equivalent to the capacity and what you can fit inside sometimes. So volume is the measure of the space that a solid figure occupies. And we're going to be taking a look at all those together. All right, so first we have a problem because we're not only learning about shapes, but how these shapes and what we learn about them fit into real world problems. So the Castle dei Monti in Apulia, Italy, was built more than 750 years ago. The fortress has one central building with 8 surrounding towers. What polygon do you see repeated in this structure, and how many sides, angles, and vertices does this polygon have? And we're going to look at it in a second. A polygon is a closed plane figure formed by 3 or more line segments that meet at a point called vertices. They're named by the number of sides and angles that it has, and to identify the repeated polygons in the fortress, you're going to complete the table below. So we're going to take a look at the fortress, but first we need to learn what a polygon is. So here's your polygons, and I just want you to pause the video and just sort of study what makes these polygons. And first I'm going to give you a clue. They're the fact that their shapes are closed. So take a look at the words, any new words that you're not sure about, and I want you to just sort of write first what you think, and then afterwards we're going to talk a little bit and fill in the chart. All right, so we're going to take a look at the sides, angles, and vertices of what makes polygons. And remember, a polygon is a closed plane figure formed by 3 or more line segments that meet a point called vertices, and it's named by the number of sides and angles that it has. So let's take a look at what makes these plane figures, and let's take a look at the sides, angles, and vertices and how they relate to the names of these shapes. Some of these shapes you're pretty familiar with, and we're going to break them up by the columns. We're going to take a look at the sides. And what is a side, angle, and vertices? Well, the best way to think about it is a pair of scissors. Vertices that have a V, all right, see your V, these are these points. These are the points on the shapes. And if you can imagine, if you could touch them, if they weren't on a plane, a flat plane, they weren't two-dimensional, you would actually be poking your finger on them. So vertices, which have your V, are actually your points on these shapes. Your angles are inside. They're this part inside the shape that they make. And then the sides, if you think about the outside, I almost feel like a sides has an S, which means if you were rubbing along, you can hit like a paper cut or a paper slice. So vertices are those points. You make a V and you have those points at the top. Sides are the slicing part, and angles are what, when the sides come together, they actually create an angle. All right, so we're going to take a look at what each of these have in common. So your triangle has one side, two sides, 3 sides. All right, so if I was to rub my hand along on my side, now you notice I put one line. Well, if I was, I want to do this well. One of the symbols that they use to show you if the sides are the same length are these dashes. So if I have 1 dash here and 2 dash here, that tells you that these sides are not the same length. Well, do you notice this one's a little bit longer? So this one would also have a dash, and that would tell you that none of these sides are the same length. None of these are the same distance from each of their vertices. So I would show that this way. Now, so our blue is going to be our angles, or excuse me, our sides. So let's take a look at our angles. Those are the inside ones. All right, again, this is our inside. So we have 1, 2, 3 sides, and we have 1, 2, 3 angles. So I know that this is a polygon because it's all closed in, and it has 3 sides, more than 2 sides, and it has 3 angles. So the vertices again are these points right here. 1, 2, 3. So this triangle, which has the root word tri for 3 and angle, isn't that interesting? It has 3 angles, and that's why it's called a triangle. It not only has 1, 2, 3 sides, 1, 2, 3 vertices, but it has 1, 2, 3 angles, and it is a closed shape. It's not open, and what I mean by that is I could draw an angle that has 2 sides and draw a third angle. So here's my angle, here's my angle. It has 3 sides, but it's not a closed shape, so that is not a polygon. Remember, polygon has to be closed. All right, so let's look at a quadrilateral. Well, you probably know the root word quad, like in quad runner, stands for 4. And does that have any relation to the shape? Well, let's take a look. Again, it has 1, 2 sides, and I'm putting 1 line for each of them because guess what? They're the same length. 3 and 4, and I put 2 dashes here and 3 dashes here because they're not the same length. So in my shape, even though I'm not the best artist, I want to let you know that these 2 sides are the same length, so I'm using 1 hash or 1 dash, and that this top one is a different length than all 4 of them, and this one is a different length than all 4. So this 4 quadrilateral has 4 sides. How many angles does it have? Can you count them really quickly? 1, 2, 3, 4. And then how many vertices? If I was to poke my finger on them, 1, 2, 3, 4. So being called a quadrilateral is not a mistake. All right, it has 4 of it has 4 of everything, right? Triangle has how many? Tri stands for 3, tricycle. So a quadrilateral has 4. All right, so let's take a look at a pentagon. Do you know the root word of this? Yep, that stands for 5. So if this works well together, everything should have 5. Well, let's take a look at our sides. 1, 2, 3, they're the same length. 4 and 5. So 2 of these have the same length. These 2 have the same length, but they're not the same as this one and this one. Fifth one has the same length. On here, if I was a perfect drawer, a perfect artist, each of those would have the same length. So there's different ways to show these polygons. Even this quadrilateral can have a different shape. But this pentagon, it just needs to have 5 sides. And how many angles? 1, 2, 3, 4. And then believe it or not, this is your 5th one. I know that's a weird one, right? You remember what name that angle is? It's a very obtuse angle. All right. So it has 5 angles. This one has 5 angles. And then if you were to poke yourself on the ends, 1, 2, 3, that's not a really pokey one, 4, 5. And 1, 2, 3, 4, 5. So your pentagon, which has the root word pent for 5, has 5 angles, 5 sides, 5 vertices. Quadrilateral, which has the root word quad, stands for 4, has 4 sides, 4 angles, and 4 vertices, just like a what? You're right. A square is a quadrilateral, as is a rectangle is a quadrilateral. Triangle, 3 for the word try, 3 sides, 3 angles, and 3 vertices. So what do you think hex means for hexagon? If you said it meant the number 6, you would be totally correct. And again, if I was a perfect artist, my hexagon would have 6 perfectly equal sides. But in this case, my drawing kind of lets me down. But at least my symbols will tell you that they're supposed to be equal. And my angles, how many do I have? 1, 2, 3, 4, 5, 6 for hexagon. And how many vertices do I have? 1, 2, 3, 4, 5, 6. All right, so again, tri for 3 has 3 of everything. Quad for 4 has 4 of everything. Pent for 5, pentagon 5, hexagon, and so forth. So keeping that in mind, let's go back and take a look at our other shapes to see if we can figure how to fill those in. Pause the video and fill all these boxes in. So heptagon stands for 7. So now what should you have if that rule is true? You should have 7 sides for 7. You should have 7 angles. Now remember, some of them can be obtuse. So they won't always be these ones that sort of bend in towards each other. They may be ones that open out. They're larger than 180 degrees, if you can remember that 4th grade. Your acute ones are less than 90, and your 90 degrees are 90 right angles. It should also have how many vertices? 7. Octagon, right? Octopus, all that stands for 8. So what should there be? 8, 8, and 8. Well done. And a nonagon, nona stands for 9. That's what my grandkids call me. Nona stands for 9. And it should have 9 sides, so go ahead and count them. 9 angles and 9 vertices. And a decagon, from your decimal, your decameter, all those D's, DECs that stand for 10. You're right, it should have 10 of everything. So go ahead and count them. So sometimes they are greater, the angles inside are greater than 180. Remember, those are your obtuse angles, and that's why it's a little bit harder sometimes to find them, what you recognize, because we're so used to seeing these smaller ones. But you can have obtuse angles inside these shapes, so just keep that in mind when you're looking for them and helping find the vertices, because the vertices are the point at which the 2 sides come together and make angles. All right. And then what pattern do you see among the number of sides, angle, and vertices that a polygon has? So do you see the pattern that you made? Well, if you filled them in, it should be, let's take a look. That triangle have 3 sides, 3 angles, 3 vertices. What did that quadrilateral have? 4 sides, 4 angles, 4 vertices. What did that pentagon have? 5 sides, 5 angles, 5 vertices. And what did that hexagon have? 6 sides, 6 angles, 6 vertices. So what you should see on your chart when you fill it out is there should be the same number all the way through for your shapes. How'd you do? So now with that in mind, you should have filled yours out. With that in mind, let's take a look at our original problem. What it says, which polygon do you see repeated in the structure? How many sides, angles, and vertices does this polygon have? So when you step back, you can see the larger shape that kind of falls to the side. And yes, there are many other shapes inside of it, but I think it's looking for the larger shape that it has. So can you see what it is? Let's count. Let's start right here. 1, 2, 3, 4, 5, 6, 7, 8. It has 8 sides. 1, 2, 3, 4, 5, 6, 7, 8. It has 8 angles. And 1, 2, 3, 4, 5, 6, 7, 8 points, 8 vertices. So you have, there's a couple other shapes if you notice. There's squares, there's triangles. I mean, you can get pretty complicated. And look, 1, 2, 3, 4. You actually also have a quadrilateral in there too. But I think it's looking for the larger one. And it says, what shape is repeated? The octagon is a repeated polygon in the Castle del Monte because it has 8 sides, 8 angles, and 8 vertices. But I would argue you could have also said there were some repeated triangles, some repeated quadrilaterals, and some repeated squares. But I think it really wants the octagon because it's saying that it's repeated not only in the building but also in the towers. All right. So regular polygons are when the line segments have the same length, or when all the angles have the measurements that are congruent. So that's where I was using, remember those similar dashes to show it. So on these two, they have the same length, so they each have 1 dash. On this one, they have 2 dashes, so these two are the same length. But these lengths are not the same as these two. And then they also did the same thing for the angles. Do you see that? So these two angles, because they have the same number of lines, are the same measurement, and these two right here are the same measurement, but they are not, all four aren't the same. So a regular polygon has to have everything the same distance for each side, and the same measurement for each angle. So that's a regular polygon, all right? But a not regular polygon is when you might have a couple sides that are the same length, there are a couple angles that are the same measurement, but all of them are not exactly the same. So these two here are the same, but they're not the same as these two at the bottom. And that's what those angles help you understand. So what I want you to do now is take a look at congruent parts. So label this Venn diagram to classify them as a regular polygon or an irregular polygon, and then say what each one has congruent. So in the middle you have everything, right? So you have all the sides the same and all the angles the same. So which one of these has the same sides and which one of these might have the same angles? So just think about that and you're going to fill that in. So use your Pear Deck. Okay, go ahead and pause your video. All right, so what I noticed for this one is all of these have congruent angles. Do you see that? They all have 90-degree angles on this side, but their length of their sides are not the same. So I'm going to say that these have congruent angles, and I can write out the word angles, or I can just use the symbol for angles. Now inside of here, they're regular polygons, and you could type in the word polygons, all right? I'm just going to put P for polygons, because look at this. They have the same size. I can tell same size sides, the same length of sides because they have the 1 dash, and they have the same size angles because they all have the same number of lines that represent the measurement of the angles. See, these are right angles. See the squares? And each of these has 1 dash, so they're the same length. Now, what is the same here? Are the angles the same? Well, these have 2 sort of arcs, but this one only has 1, and this one has 1. So these 2 are the same measurement. But they're not the same measurement as these two, even though these 2 are the same. So this one does not have congruent angles, but look at the sides. Each side has 1 dash. So I know this one has the same side, length of sides, but not the same angles, but look at this one. Same thing here. All the length of the sides are the same, but the measurement of the angles are different. So this one has congruent sides. And again, I don't know why they didn't use the word equivalent. So this is a new vocabulary word of congruent, which means same measurement, and we are using it again. So explain how the group of polygons in the center section of the Venn diagram is related to the group on the left and the right. Well, if these all are shapes that have the same size angles throughout, then the ones in the middle also have the same size angles throughout. If on the right side they have the same length of sides throughout, well then the ones in the middle should have that as well. So the ones in the middle have both properties, both features, but these on this side only have the feature of the same measurement for angles, and these only have the feature of the same length of sides. Oops, sorry, it's supposed to change. It's not changing. Name this polygon and use the markings on the figure to tell whether it's regular or not regular. Give it a go. Let's take a look. You should have your entries here, and let's see what we come up with. What's the name of this polygon? Well, remember the name is reflected in the angles, and I noticed there are 1, 2, 3 angles. So what is that root word for 3? Tri. So this is a triangle polygon. All right, and I know it's a polygon again because it's a closed shape, and I know it's a triangle polygon because it has 1, 2, 3 triangles and 1, 2, 3 sides. The next question it asked you, is it a regular polygon? Well, if it's a regular polygon, all the angles and all the sides need to be congruent, and congruent means that they are what? The same measurement. All right, are they? Well, I can tell by my symbols that they are. These markers, because they're exact same number of dashes, mean that these are the same length, the same distance from each vertice. Remember that? And that each angle also has the same style. So these angles are also the same measurement. All right, how did we do? So is it a regular one? Yes. Are all the sides and on the angle congruent? Yes, which makes it a regular polygon. All right, so name each polygon and then tell whether it's a regular or not regular polygon. So go ahead and pause, and then we will see how you do. All right, how did you do? So first, this was a regular polygon because take a look. All the angles are the same measurement. I could tell because they're using the same number of arcs, and all the sides have the same length because again, they're using the same number of dashes. In this case, it's 1. Remember, those vertices are those points where if you could kind of touch them and poke your finger. And so your sides are those long lines, and your vertices are those points that kind of create V's. Number 3, it's just a polygon, okay? But you can see that the angles are the same measurement. They're using the same kind of style, and that's actually represents a right angle. But the top and the bottom have 1 dash, but look at the sides, they have 2 dashes. So the top and the bottom are the same length, but they are not the same length as the sides. What about this one? Well, first of all, this one was a 1, 2, 3, 4, 5, 6-sided figure, which made it a hexagon. Okay, so it's a regular hexagon. Hex stands for 6. 1, 2, 3, 4. 4 is a quad, right? A quadrilateral. Can't say that today. Quadrilateral, sorry. And then this one has what? 1, 2, 3, 4, 5, 6, 7, 8. So this is a regular octagon. Octagon. Oh, I can't even spell tonight. There you go, octagon, polygon. Because all of the same sides and the angles have the same measurements. Do all regular pentagons have the same shape? Nope. Okay. This one is a hexagon. This one is a octagon. They're different shapes. I could have made this into a square, right? If that was a square, all of them would have the same length of sides as well as the same length of as well as the same measurement of angles. Here, let's see if I could do that really quickly. Can I draw a square pretty quickly? It has to be a perfect square, right? Is that perfect? There you go. So there's another regular polygon. That's not a sorry. All right, moving on. I'm a terrible speller. All right, next one. All right, so now we're going to do your homework. You're going to go ahead and do the problems, and you can check back for the answers. Work through them as much as you can first, and then come back for the answers. All right, how did you go? So this one was a regular polygon. It was a regular quadrilateral with 4 sides that were the same length. I could tell by the dashes, 4 vertices and 4 angles. They're all congruent or equal because even these sides are the same. See how they have the same shape? In this case, they're right angles. That's represented by a square. Number 3, it's not. It does actually have a shape that has the same, that has congruent angles, but take a look at the lengths of all the sides. These two are the same length. These apart ones, distant ones, are also the same length. These two are, but the longest one is a different size than all of them, and this one is a different size. So it is a octagon. It is a polygon because it's a closed shape. It does have 8 sides, 8 vertices, and 8 angles, but they are not all congruent and equal. And last but not least, 1, 2, 3, 4, 5, 6. 6 is hexagon. This is a regular one. Every length of every side is the same. You can tell by the 1 dash, and all the measurement of the angles are the same. So keep going. Go ahead and give these problems a go. Pause your video and then come back to see how you did. We have one regular polygon right here. It's a triangle, a polygon again because it's a closed shape with more than 2 sides. It has 3 sides that are the same length. It has 3 vertices and 3 angles. And I know they're the same because of the 1 dashed all the way around and the same number of arcs. So they're equivalent or equal in measurement. However, this is a pentagon. It doesn't look like a pentagon, right? But it is 1, 2, 3, 4, 5 sides. Again, a polygon because it's closed. It does have the 5 sides. It has the points 1. This is an obtuse one, 2, 3, another one, 4, and 5. Has 5 angles and 5 vertices. 1, 2. This vertex is pointing inwards. 3, 4, 5. But they are not all the same. These angles have the 2 arcs. This one has 1, so I know those are not the same angles. And if I was to put one here, or around this side actually, that would be a very large angle, would not be the same measurement as these other ones. The distance of the, or the length of the sides are also distance. These two have the same length, these two have the same length, but they're not the same together, and this one is definitely longer than all of them. All right, next problem. How are you doing? All right, so now you're going to sketch 9 points that connect the points to form a closed plane figure. What kind of polygon did you draw? And then you're going to sketch 7 points. What kind of polygon did you draw? So you can draw these here on your pear deck or on your own paper, bring them in. The most important thing is yours all will look different. To be a polygon, just remember it needs to be closed. It needs to be closed and those sides need to be straight. All right, name the polygon, right, whether it's regular or not regular. So go for it. All right, so this one is your regular polygon. It's a pentagon. Pen stands for 5. 1, 2, 3, 4, 5. All the sides are the same length and all the angles. This one is a 1, 2, 3, 4, 5, 6, 7, 8. So this is an octagon, polygon again because it's closed. But I noticed it has 8 sides, 8 vertices, 8 points, 8 angles, but they are not all equivalent or congruent in measurement. I noticed the angles definitely look like they are, but these sides are the same length as these 2 sides down here. So 4 sides appear to be the same length, but these 2 ones across are not the same as the top, and these ones at the top and bottom look a little bit smaller, so they're not. So the angles are congruent, but not these sides in that representation. All right, so keep going on. You're just about done working on your spiral review. Go ahead and read through the problem. I'll read it to you while you're thinking about it and work it out, and I'll show you the answer. Anne needs 42 feet of fabric to make a small quilt. How many yards of fabric should she buy? And number 4, Todd begins piano practice at 4:15 p.m. and ends at 5:50. How long does he practice for? So think about the strategies you use for those. Hopefully you worked out these problems, so let's take a look ourselves. I'm going to make my screen a little bit bigger. All right, this is our review. This is our, review, so it's really nice. This is our measurement conversion. So I'm going from feet to yards to find out how much Ann buys. So first I'm going to make my table, and I'm going to go from feet to yards. I'm going to put what I know. Now this is memorization. Do you remember how many can you do yards into 1 foot or 1 yard into 1 foot? So I'm going to just show my bar graph, what goes on top. My biggest measurement is a yard, remember, and it's broken up into how many feet. 3 feet. And remember, some of you might want to go on and say how many inches. 12 inches for each foot, so 36. But right now we only need feet and yards. So 1 yard is 3 feet. And remember, when you're going from the smaller number to the larger number, you're multiplying by 3. 1 times 3 is 3. That's how I got my 3 feet. If I go this way, 3 divided by 3 would give me my 1. Or remember, what we were picking up is that's the same as multiplying by 1/3. So we're just keeping that in mind, that dividing by 3 is the same as multiplying by 1/3. So if I have feet, I'm going to be multiplying that or dividing them to get my yards. If I was to have my yards, I'm multiplying them by 3 to get how many feet. So what do I have up here? I have 42 feet. So I'm going to put that in my chart. And I know the operation that I use to do that would be dividing by 3. So that's where you're going to have to use your division strategies. So how many 3's can I take out of 4? 1. 1 times 3 is 3. 4 take away 3 is 1. Bring down the 2. How many groups of 3's can I take out of 12? Hopefully you know your multiplication tables. 3, 6, 9, 12, 4. 4 times 3 is 12. 12 take away 12 is 0. So I can take out 14 groups of 3. 14 sets of 3 feet to get my yards. So 42 feet would equal 14 yards. So my solution statement is Anne buys 14 yards. So remember, these are the measurements. You got to start memorizing those symbols. All right, let's take a look at Todd. So here I used a conversion chart, but Todd's playing the piano. He starts at 4:15. He ends at 3:50. How long does he go for? So remember, for time, elapsed time, we said it's really good to use a number line. So I'm starting at 4:15 and I'm going to 5:50. Okay, PM, that's awesome. I'm not going over. So the first big jump I can make is I can make 1 hour, right? That takes me to what? 5:15. So he's been practicing for 1 hour. What's the next big jump I can do? Well, I know if I go for 15 minutes, that'll take me to 5:30. So I've now gone 1 hour and 15 minutes. Well, the difference between 5:30 and 5:50 is what? 20 minutes. So I'll put that up here. So that 20 minutes would take me from 5:30 to 5:50. So from 4:15 to 5:50, I went 1 hour, 15 minutes plus 20 minutes more. So what is 15 plus 20? 5 plus 0 is 5, 3 plus 1 is 3, so that's 35 minutes. So altogether, my total is 1 hour and 35 minutes. And that's how the number line helped me. So how long? There's my solution statement. Todd played or practices for 1 hour and 35 minutes. All right? All right, let's try the next problem. Problems, I'm not going to read them out loud for you, but remember how I pulled apart all the important information, so make sure you write that down in your book, or you can use your Pear Deck and underline it. But pull apart the information, and then I'll work it out for you. So pause the video, work these 2 problems out, and then come back. Hopefully you worked out these 2 problems. So I pulled out the information. Jenna had 30 barrettes. She's organizing them into 6 boxes. She puts the same number in each box. But here's the trick. Write an expression you can use. So it's not just finding the answer, it's writing the expression that they want to see. All right, so I'm going to act it out. Jenna has 30 barrettes, and she's going to put them, actually let's use our bar graph, right? Let's imagine that this was 30. So she has 30 of these barrettes, and she's going to put them into what? 1, 2, 3, 4, 5, 6 boxes. So she's going to put these 30 barrettes into 6 boxes. Well, using our bar chart, what does that show you? What operation is that? We're going to break it up into 1, 2, 3, 4, 5, 6 boxes. It's division, right? So I'm taking 30 and I'm dividing it. Remember, fractions are division. Dividing it by 6. I'm taking 30 and I'm dividing it by 6. I'm taking 30 and I'm dividing it into 6 groups. So how much is that? What number times 6 will give me 35? All right, so we need the expression. So honestly, I think that's a good expression, but this is probably more what they are looking for. Now, if I have the equal sign, then that's an equation. So the expression would be 30 divided by 6. Now, if they normally will go on to ask you for the answer, so you would give that as your expression, and then you would go on to answer the question that way. And remember your solution statement. How many are in each box? There are 5 barrettes in each of the 6 boxes. Boom. Remember that solution statement, that SS. All right. Or that was Jenna. Sorry. Melody's over here. She has $45. She's spending this much. Then her mom gave her this much. So I'm going to again go back to my bar chart. She has $45 altogether. She's going to spend, try to make it more realistic, $32.75. So she's taking that away. Do you see that? So I don't know how much she has left here. But then mom's then going to give her $15.50. So just by kind of mapping it out with my bar charts, I can see what I need to do. I need to first take away $32.75, and then I need to add to that $17.50 to find out how much she has now. All right, so if I put $45 down and I need to take away from it $32.75, what do you notice? Okay, that's not an accident they're doing that. Remember that decimal point is the difference between your dollars and your cents, your place value, your parts and your wholes. So I need to line up my decimals, and I need to actually add those 2 zeros that represent your tenths and your hundreds, or your dimes and your pennies. All right, can I take away 5 from nothing? Nope, I can't even borrow from here. There's nothing. So I'm going to go all the way to my ones. I'm going to borrow $1, and I'm going to create 10 dimes. That's still not helping me with my pennies, right? I can't take away 5 pennies from nothing. So I'm going to borrow from my 10 dimes, leaving 9 dimes, and breaking that 1 dime into 10 pennies. 10 pennies take away 5 pennies is 5. 9 dimes take away 7 dimes gives me 2 dimes, which is 20 cents. So I have 25 altogether. $4 take away $2 is $2. $4 take away $3 is $1. So after she spent that $32.75 from her $45, she has $12.25 right here. That's what makes up the whole number of 45, right? But now her mom went and gave her, which is addition, $15.50. So she's adding that to that amount. 5 pennies add nothing is 5. 2 dimes add 5 dimes would be 7 dimes, or 70 cents. So that's 75 cents altogether. I always put my decimal right down, separating my dollars from my change. $2 add $5 is 7, and $1 add $1 is $2. So how much does Melody have now? Here's my solution statement. Melody has $27.75 now. Boom. All right, so how did you do? This was a long video because we were just introducing polygons for the first time. So hopefully it worked out pretty well. I know it was kind of long. We'll start some of this in class. But I want you to think about how you could identify your shapes and how did we classify them? How did we know the name of a shape? What were those clue words? And how did we organize them into regular and not regular polygons? What were the common features that they had? All right, so write that on your Pear Deck. And last but not least, how do you feel about your polygons? How do you feel about starting to name them? How do you feel about understanding what the parts of them are? And how do you feel about being able to classify them into regular and irregular? All right, I'll see you tomorrow. Have a good day.